we're just going to take a minute to talk about matter. When we talk about matter, it's important to remember that matter is basically anything that has mass and takes up space, right? The first thing that we did when we started talking in this unit was we discussed the word chemical. And sometimes people call all sorts of things chemicals. Uh, Cleaner might be chemicals or gasoline, you know, all of these things are examples of chemicals. Patriotism, electricity, sound, jealousy, love, these are not chemicals, but everything else here are examples of chemicals. One of the things I get upset about is when people think that the word chemical means something bad. And that's not necessarily true because, of course, pure water is a good example of chemicals. Sugar is a chemical, and I certainly like sugar, so that's not bad. So the word chemical is just means a variety of things that are chemically bonded together, which we don't exactly know yet, but we can define what a chemical is. Then we organized the elements based on their properties. And this directly is going to start to correlate to what we're going to know as the periodic table. But when we looked at these properties, we found things like physical properties versus chemical properties, right? So physical properties are examples of things like soft, hard, silvery, brittle. Brittle means if you pound it with a hammer, it'll break easily. Metallic means it has that shine. And then chemical properties and all involve reactions. Reactions to acid, reactions to water, reactions when things burn. These are all examples of chemical properties. We also saw that different elements have different densities. Densities, of course, are grams per centimeter cubed. That's a mass per unit of volume. And it doesn't matter how small the piece is or how large the piece is. That's why density is what we call an intrinsic characteristic. And then MP and BP stood for the melting point and the boiling point. And these were all listed in Fahrenheit, which kind of annoyed me because they should be in Celsius, which is what we would use in science class. But you can see a huge variety here. This is 15,000 degrees, or I'm sorry, 1,500 degrees Fahrenheit, as opposed to chlorine, which has a negative 150 degrees Fahrenheit. That tells me that chlorine exists as a gas at room temperature. And that's one of the last things that we saw there was its state of matter at room temperature. We saw solids and we see some gases. That's the state of matter at room temperature, what we're normally going to find it at here on planet Earth. So again, just to review, chemical properties are its reactivity with things. This includes things like reactivity with water or reactivity with acids. And then another thing that it can be reactive is if it's flammable. Okay, so is it reactive? Is it flammable? In order to observe a chemical property, it must be observed during a chemical reaction. A second type of property is a physical property: size, shape, mass, color, shine, malleability, density, melting point, boiling point. State of matter: is it a solid, liquid, or a gas? And the last one that's a little bit different that we haven't talked about too much is solubility. Does it dissolve in other substances? We often talk about, does it dissolve in water? Like sugar does a nice job of dissolving in water. That's a physical property. So if we're talking about properties, it would be natural that we then would talk about changes. So there are chemical changes versus physical changes. In chemical changes, we're going to have those reactions happening. We're going to have it react with other substances. We're going to have that flammability happening. It's going to burn. Physical changes are changes in the size, the shape, the mass, etc. When it melts, when it boils, these are physical changes. Remember, when water boiled, It was still water. When water froze, it was still water. We just called it solid water, which sometimes people call ice. And then finally, the one I was just talking about, solubility, when things dissolve, those are examples of physical changes. Now, how do we know whether it's been a physical change or a chemical change that's taken place? One of the things I tell students is if the substance still exists, it probably was a physical change. If it's still water, it probably was a physical change it went through. But if a chemical change happened, then it's going to change into something different. And there's some indications that a chemical change has happened. The color might change, it might heat up or cool down, gas might be released. We see this as bubbles, or a precipitate is formed. This is not like a precipitate, like precipitation outside in the rain. Instead, this is something really interesting in chemistry where a solid forms from two liquids. So you actually put two liquids together and a solid forms. Now, if it heats up or cools down, this is examples of an endothermic or an exothermic reaction. An exothermic reaction is going to mean that heat is going to exit the system. That's why I like the word exit, like exo. Heat exits the system. It releases energy in the form of heat to its surrounding. That's an exothermic reaction. An endothermic reaction is one that absorbs energy from its surrounding. The system is going to give it energy. It's actually going to get cold. It gets cold when it's an exo or an endothermic reaction. One of the things that's a little bit confusing is when we look at ice cubes, right? Remember that example way back at the beginning of the year where we talked about ice cubes in the freezer? And when ice cubes were freezing in the freezer, it actually has to release energy into the environment. Refrigerators actually warm up a room. That's because when things are freezing, and if you remember back to our favorite graph here, where we have, remember, we have temperature over here, and we have heat down here. The ice heats up, the ice melts, the liquid heats up, the liquid boils, and then the steam heats up. If we move in this direction, this means it's absorbing heat. It's taking heat in. We're moving from this amount of heat to this amount of heat. So if it's absorbing heat, that's when things are melting. And that would be a good example of that would be an ice cube. The opposite of that would be in this direction when things are freezing, and that's right here. Now, I know what you're thinking. You're like, Ms. Robles, this doesn't make any sense. Freezing does not heat up the surroundings, but it actually does. And at the same token, you might be thinking, but melting is not when things get cold. Melting is because things are getting hot. Well, no, you're thinking about it backwards. Melting is happening because we are adding heat. If it's taking in the heat from the surroundings and a chemical change is happening, it's actually going to feel cold. A good example of this would be something like an ice pack. So anyways, I encourage you to take a look at these because these can be kind of tricky. Let's take a look at another characteristic that we looked at, metals versus nonmetals. If we go back to those cards there, you'll see that some of these are labeled metals, like sodium, and some are labeled nonmetals, like phosphorus. On our periodic table, there is a line. Okay, we sometimes call this the staircase in the periodic table, and it goes right here. And to the left of this entire staircase, this whole side here, including all of this, those are the metals on the periodic table. And to the right of the staircase, those are all the nonmetals on the periodic table. So you might be wondering, what are these yellow things? Those are called the metalloids. They're a little bit metal, they're a little bit nonmetal, and generally they touch the staircase, with the exception of aluminum. We've seen aluminum foil before, we know that that's a metal, but metals have certain characteristics about them. They're shiny, they're malleable, and nonmetals have certain characteristics about them. They're not shiny, they're dull, and they're brittle. And metalloids are kind of interesting because they're somewhere in between. So now you can always look at the periodic table and tell what's a metal, a nonmetal, and a metalloid. We also talked about solids, liquids, and gases. Now, if you take a look at the periodic table here, this is the elemental states of matter at 25 degrees Celsius. That's about room temperature, okay? That's what we consider room temperature in chemistry class. So here are our gases. Here are all of our solids. There's a lot of them. And then there are only two metals on the periodic table at room temperature. One is mercury, is a metal, and the other is bromine. Bromine is a nonmetal. Here is a picture that needs no explanation. I think that we covered this a lot in Unit 1, but here's the difference between a solid, liquid, and gas. A solid has a fixed shape, a fixed volume, and a gas has no fixed shape, no fixed volume. It fills that entire container. A liquid, again, somewhere in between, but it does have that fixed volume. That's why we sometimes will say that solids and liquids are closer to each other. It has to do with that fixed volume. Solids and liquids also share the fact that their particles are fairly close together, and that's because of that fixed volume. Here's words that we remember from the first unit, right? We have freezing and melting, and evaporation is a type of vaporization. The opposite of that is called condensation. And here's two that we did not talk about yet, but you can start remembering them. Sublimation is when a solid goes directly to a gas. The best example of that is dry ice. And if you don't know what that is, that's okay. We will actually look at it. And then the opposite of that is deposition. But as you can see there, the states of matter can flow all around. I want to point out to you that usually, so far in your life, when we've been talking about this, we've been talking about water. But as pointed out over here, all elements can go through all these states of matter. So neon, for example, is sitting at a gas. If we were to condense neon, it would be liquid neon. Okay, so start getting out of the mindset that this is just water. Water is just one substance on Earth. Back to the periodic table. I want to make sure that when we talk about it, we're using the same language. Groups run this way in the periodic table, right? So these are the group 1 elements, the group 2 elements, and then we go 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, group 17, and group 18. Groups are sometimes called families, and I'll talk about those in a second, but they're pretty important because we're going to find out that these guys all will share characteristics with each other. In this direction on the periodic table, we call these periods. So, for example, this is the first period, second period, third period, and so on the periodic table. This might be a good point to point out to you, this little spot right here. This belongs in there. The reason it's not in there is simply because it doesn't fit nicely onto a piece of paper. All right, it's nothing special. It's not anything fancy. It just would fit right into there, and that's why these colors match up with those. They are actually in the same period, in those same horizontal rows. So back to groups. Groups share common properties. So this is a picture of the periodic table kind of squashed together. This is the spot that's been squashed together. You can look on your periodic table. Sometimes we'll see this version of it in chemistry because those transition metals don't matter as much. Anyways, these are the group one elements. Those group one elements share characteristics and common properties. We have started to see this already. We've seen that sodium and potassium both explode in water, right? As well as rubidium and cesium. Okay. We know that magnesium and calcium, they don't explode in water, but they have interesting reactions with water. We're going to see some common characteristics between these elements. So these groups and families are more important when we're talking about relationships than the vertical or the horizontal rows that we call periods. Let's talk about matter. All right. So at the very beginning of the unit, when you did what is a chemical, you looked at maybe a red ball and a red ball, and it was attached to a black ball. Okay. So maybe that's something that you looked at. So what was that? Well, matter can be separated into two major categories: pure substances or mixtures. Pure substances can be either elements or compounds. So in this case, I drew a compound. If you have several of the same compound together, that's a pure substance. A good example of that we've used over and over and over again would be water. Water is a pure substance. You also can have a pure substance that's just one type of element, like maybe you have oxygen, or maybe you have neon, or something like that. Then on the other side of things, you have mixtures. You can have two types of mixtures. Homo means the same, and hetero means different. Okay, so you can have homogeneous mixtures, which are roughly the same throughout, and heterogeneous mixtures, like this picture, where it's kind of piled up at the bottom and there's different things here that are different. So a homogeneous mixture, I don't know, might be air is a great example of a homogeneous mixture, or salt water that's all dissolved and shaken up is a good example of a homogeneous mixture, where salad dressing is a good example of a heterogeneous mixture. So this is all of matter and how we can classify it. Here's another example of those ball and stick models. Here is an element. Those are just single balls. I want to also point out to you that in the case of, say, some substances, specifically oxygen, which is represented with red sometimes, you can see them stuck together. And just because there's two or more that are bonded together, that also makes them elements. Okay, so they don't have to just be one, they can be two. So oxygen joins in pairs, and these are both examples of elements. And then in this case, these are pure compound or pure substances. Compounds are two or more different elements that are joined together. So in this case, we've got carbon dioxide or CO2. This one was O2, and this is just argon. And then a mixture would be mixtures of compounds, mixtures of elements, or mixtures of elements and compounds. One last thing I want to show you that I kind of want you to memorize from the periodic table, because this will be back over and over and over again. I call it the H7 Club. And I call it the H7 Club because there are 7 of them. They make a number 7 if you look on the periodic table, and they start at number 7, nitrogen. Okay, so the H7 Club are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. And the reason I'm telling you about the H7 Club is because these elements are diatomic, which means when they travel around, they always come in pairs. So they always will exist in diatomic pairs, okay? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. I know from biology that you have seen O2, all right, because we've talked about photosynthesis and CO2. You may have wondered, why is it always O2? Why isn't it ever O? Or maybe like O3? And that's because it's part of the H7 club. It's a diatomic molecule. So